Okay, so I've got a dumb little building, real simple. You know, it's got 4 walls, a roof, floors, few interior walls. Notice that I didn't bother drawing interior doors. They do not impact the energy simulation, so it doesn't matter. It has windows. And so that's what you need to do an energy simulation. I would suggest that you do one with the courtyard house that you designed. Pick your favorite of those 3 and use that for your energy simulation test. But we'll kind of walk through doing an energy simulation here. So, so the first thing we have to do is we need to set our location. So if I click on this, I can set the location. It's kind of fun to pick places. Well, you could pick College Station if you wanted to. I think you can get Hvac. Spell it right. Yeah. So Hvac is very near Crossways. Crossways is down here, but Hvac there's pretty thorough energy and climate data for, so we can use Hvac for this study. So if I've got Hvac, I could pick this one down here. It's a little bit closer to Crossways. So that looks like that one right there. So, so I'll pick that one, and that's our location. And we'll design for that. So, so we're picking the location and setting the location. Obviously, the location is the climate. And so it absolutely, totally affects the building design, the energy performance, and so on. So we can set the location. I'm going to save this model as a new name. So it'll be more like you starting a new project. So I'll say Insight Test 2. And in the next step, well, so anticipating doing this, you know, I've set up room objects, and I can add a color scheme just to make that more clear. So rooms by name, all of them have the same name, so it's kind of dull, but so you can see we have room objects. One thing I learned from doing this study is that you can actually apply a color scheme to a section view, and so it creates colors for each of the rooms, color fill for it. Add a legend. I don't know. It might be a little more interesting to give rooms names. So, okay, so now they're all color coded, and if we go to that view, we can see how even in section they're color coded. Thing I need to do is go into this analyze and spaces and zones and click on area and volume calculations and make sure that areas and volumes are turned on. So energy simulation is clearly a volumetric thing. So doing only area calculations is not quite good enough. So, so I'll turn on areas and volume calculations. Now the next thing to do is go here to energy settings. And here there's a lot of settings here. So you'll notice the mode is use conceptual masses and building elements, or use building elements. So by using conceptual masses, you don't even have to put walls on your buildings. You can just do the massing model and run an energy simulation of that, which is, a good strategy. In our case, we've probably put the exterior walls in place. We could put interior walls in place, but we have the conceptual masses, so we could use both of those. When we use building elements, we've drawn everything. So at the final stages of design, after you've done design detailing and everything, maybe you use building elements. These other settings you probably don't need to worry about. Set a ground plane. Project phase, you can actually in Revit set up multiple phases for your project. So as built, new construction, phase 2 construction, phase 3 construction, so on. Most of the time you're not going to bother with that, so new construction is fine. These space resolution things, just leave them alone, don't touch them. None of those matter. But in advanced options, it starts to matter again. So if I click on edit, I get another dialog. And these start to matter. So the building type is important. So the building type affects mostly the schedule for the building. So an office building by default, well, we could look at the operating schedules here. 24/7, 24/6. That means it's open 24 hours a day, 7 days a week. 24/6, 6 days a week, 5 days a week. Open 12 hours a day. Open as a K through 12 school. That means it's probably closed in the summer. So, so we've got these different schedules here that affect it. But if we click on building type, we can change that, and we could change it to a single family home. And then that's going to have a particular schedule associated with it, particular expectations. All right, we can set a HVAC system. Right now, you can just leave that the way it is. But just realize that we could change the HVAC system. Outdoor air information, you can leave that the way it is. So they're defaults for different types of buildings. Let's not worry about it for now. Export category. So we can either create spaces or we can create room objects. We've created room objects. This is a house. Let's go with rooms. So, so you'll create room objects, and then the export category will be rooms. Now, conceptual types gives us, this is for doing mass models. So if we're only doing a mass model, we have not drawn in the floors, etc., then we can tell it for where it thinks there should be an exterior wall, we'll use lightweight construction, mild climate insulation. So now notice these are not real constructions. These are basically categories of construction that have particular R values. Everybody knows what an R value is, right? So the R value, R stands for resistance, resistance to thermal flow. A high R value means high resistance, means that the thermal flow does not move very fast. So R10 would be a common exterior wall R value. R30 is a common roof R value. R30 has much more resistance to flow than R10. Windows are probably R2 or R3, very low. Now, you might also remember the U value. The U value and the R value tell you the same thing. The U value is the reciprocal of the R value. The R value is the reciprocal of the U value. So an R value of 10 would be a U value of 0.1. An R value of 5 would be a U value of 0.2. You just take the reciprocal of them. So, so that's the main one you're going to deal with this energy simulation, the R value of the construction. Now, we're not going to use a conceptual, we're going to use a schematic. And if we use a schematic, we get a very similar kind of dialogue. And it tells you what the U value is. So 4-inch lightweight concrete has a U value of 0.2245. That must mean an R value of somewhere between 4 and 5. And we can kind of scroll down through these and see the different ones. If I pull this down, I can see my different alternatives. So heavyweight concrete, lightweight concrete, exterior walls, concrete block, face brick. Okay, now it's telling us by default, the analysis properties are generated from information in the conceptual types. So, so that means that it's using the ones in that conceptual types dialog. The override here, if I click on the override, it will use one of these. So I can get more specific with it. Interesting thing about Insight is at this stage, it doesn't matter. Because what Insight does is it runs an energy analysis for all of the variations, all of the alternatives. So, so we might as well just go with the conceptual ones, I would say. So if we go to these conceptual types, and we could say what this is going to be, the mass exterior wall might be, it's probably high mass construction. They've talked about brick, so mild climate insulation, that's probably what it's going to be. Interior walls, lightweight construction, no insulation, doesn't really matter. Underground walls, mild insulation. Typical insulation of a cool roof. Let's just go with that. Mass floor. We can go with that. Mass slab, high mass construction, no insulation. All this is fairly straightforward. You know, You can look at that and you have enough knowledge to say, to make a decision on these. Double pane, clear. But like I said, it doesn't matter very much when using Insight because it's going to do the analysis with all of these variations. I told you it does hundreds of analyses. That's because it does all of the combinations in here. It's really kind of crazy what it does. So we've got our conceptual types and our schematic types. So you use the schematic types when you're ready to make a decision on how it's going to be designed and built. But right now, you don't have to make a decision. Wide open. So now the detailed elements means it will actually get the data from Revit. And just to show you how that is in Revit, if I click on this wall, and I click on properties, I see that's a basic wall. I can edit the type and look at the heat transfer properties of it. And I can look at the structure. And I see that I've set this to be common brick structure. And you'll see that it has actually calculated the resistance of this wall. And so it does those calculations for you. In environmental control systems, you probably had to calculate the R value of a wall. Well, Revit does it for you. If I go here to this little button, I get my materials, and you'll see that each material, most of the materials have thermal properties. So when you click a medium brick, you're getting all of these thermal properties built into it. You don't have to go find a table and look it up, put it in there. Revit already has it built in. So you just think about putting together your wall assembly, and Revit will take care of calculating the R value for you, or the U value.
Is there a way, after you've already built the item in Revit, to change the properties of it? Like if you have your wall settings a certain way and then you're like, oh, actually I want to use a different kind.
Yeah, really, really easy. All I have to do is, see, I've got that wall selected. I can go and pick a different wall.
Okay.
So brick on CMU. And, it changed the thickness of the wall, it changed the appearance of the wall, and it changed the thermal properties of the wall. So they're down here.
Okay.
And in structure, it shows me the whole list of layers that make up that wall. So you can create your own walls, or you can use the built-in ones. Now, it's a great question, and here's some advice about how to think about this and use it that most people don't do, but it really works well, is think about what the wall types are in your building. You're going to have an exterior wall assembly. You're going to have an interior wall assembly. You're probably going to have a plumbing wall because they typically are thicker than a non-plumbing wall because you got to put pipes in there. Maybe you've got exterior plumbing walls and they're thicker than the normal exterior wall. Maybe you've got 2 or 3 finishes of exterior wall. So we want brick here, and we want stone here, and we want so I would just create a custom wall for the project. This is by these types. Exterior type 1, exterior type 2, exterior type 3, or name them however way you want. You could say exterior finish 1, plumbing. Exterior finish 1, non-plumbing. And then draw your building with those types. Then if you redefine the type, you decide, well, I drew it with red brick, but I don't want it to be red brick. I want it to be brown brick. I just changed the type here and all of my drawing changes, right? Now I could go and select another, create another type and select it from the family pull down. But defining what the wall assemblies are in concept is a stronger way to do it, because the concept is more stable than the actual creation of the wall. So I often have these generic ones are pretty good. You typically, as an architect, how thick the wall needs to be. It needs to be 5 inches thick. Maybe it's going to be 6, maybe it's going to be 4, but let's call it 5 for now. It's going to be about a 12-inch thick wall. It's concrete block with a brick facing on it. It's going to be 12 inches. I don't know for sure it's going to be concrete block with brick facing. I don't know what kind of brick it's going to be. I don't know what the finishes are going to be. But I can use those generic ones to draw it. But I would kind of create the generic one and duplicate it and rename it. So XW for crossways, exterior, 6-inch. And then I would draw my building with that wall type. And then later on in the project, I would go in and define exactly what that looks like. So don't like how they have them. Don't know what that's about. 8 inches. And then at a later stage, I might refine that more. So it's a brick wall with 2 withes of brick. But the interior is probably going to be gypsum board. So, later on, I might go in and say, okay, well, let's change this a little bit. Duplicate. No, let's not duplicate. Let's just change it. Insert. Insert. And one of these is going to be gypsum board. Half-inch thick. And this one's going to be an airspace. One-inch thick. And I can go to preview and see what it looks like. That's what it looks like. And now everything that I've drawn with that XW exterior 6 inches just updates. Okay, other questions? So managing those U values in construction. We're gonna the next assignment 3 is going to be about construction. So we're going to get into that in detail at that point. And emphasize that right now, because of the way Insight works, it's going to do the calculations for low R value, for medium R value, for high R value. Low R value roof, medium R value roof, high value roof. It's going to do all of those combinations and help us see how they impact the energy use. The basic notion is that you pay money for R value. Higher R values cost more money. So you want to get by with low R values if you can. Okay, so we looked at the system analysis. I have an energy model and I'm going to delete it just so we can create a new one. We can skip this system zone, don't care about it. And I'll go to create energy model here. And it extracts from our model this. So it created spaces for each room, and it actually divided the rooms up into different zones. And this is the notion that it's used an algorithm to decide how the building is most affected by energy. And you'll see that this west wall is split into 3 surfaces here. One of them that is most affected by the south wall, one that is affected by this window, and one that is in a different room and affected by a window. And that effect goes back into the room to a certain extent. How much does it go back? There's no real way to calculate that. It's sort of use some experience and guess. And the software has done that for you. So it's created all these different zones in the building, which are necessary to doing the energy analysis. You'll see this zone in the middle is a long way from any window. And so the air temperature is very stable right there. Doesn't change very much depending on the weather conditions outside. Basically, windows are what affect your interior temperature. Yes, the opaque walls and roof affect it, but the windows are the major impact on the energy use. So, but you don't have to worry about this. Revit did these calculations for you, and they will work just fine the way it did them. Now, the next step is to go to generate. And so this creates the analytical model. If you haven't already created it, we've already created it, and sends it to Insight. So Insight is on the cloud, so it's a cloud service. That's why it can do hundreds and hundreds of simulations in a few minutes, because it's got incredibly powerful arrays of computers backing it up and running those simulations. If you tried to do this on your home computer, it would take you 3 or 4 days of just solid calculation time. But Insight will do it in a few minutes. So we click on generate. We can use the existing one because we already created it. and it sent it. It's probably not finished doing the calculations yet. But you know, but we'll find out from Insight whether it's done or not. So questions about that? It's pretty simple. You're just going through this set of energy optimization icons. All right, you'll go to insight360.autodesk.com, log into Autodesk. You should be able to use your Autodesk login. You might have to create a new account or something. I don't know. So so you'll log into Insight using your Autodesk account. I'm going to refresh this. And you see it's still working on my analysis test 2. Says it needs some sort of update, but it'll run anyway. All right, so this is what you get with Insight. And some key things here are the this number. So it costs $1.45 per square foot per year to heat and cool this building. And I can spin this around and look at it. Not very interesting. Looks like it's not really counting the windows. I'm not sure about that. We'll have to go back and look at that. And you see that it compares that to the relevant standards here. So ASHRAE 90.1 says that for energy efficiency, we need to try to get below $1.04. So, you know, we're at $1.45. Okay, that $1.04 is based on the standard, is based on the location, it's based on the square footage of the building. So $1.04 per square foot. And that's what we're looking at. Now, now the next step, it's a bit weird. You just work in Insight. Don't go back to Revit. Right now, you're just working in Insight to try to figure out what the best thing to do with to make this building more efficient. You know, it's very interesting. This is not really a tool for running energy simulations. It's a tool for getting insight about the impact of climate on your building. You know, Insight does that by letting you see all of your models, all of your changes that you might make. So in this case, now the other thing to realize is that Insight is giving you ranges. It works by doing, as I've said over and over again, hundreds of energy simulations. And this range here shows you what the variation of all those hundreds of energy simulations are. So if we were to use really poor insulation and poor construction, we'd probably be costing $5 a square foot per year on this building. Is that a lot? Well, this is really mild climate, so it's not a whole lot of money. But considering if we do a really good construction, we can get down to 53 cents per square foot per year. You know, so if it's a 2,000 square foot building, you know, that's $1,000 a year on energy, which is pretty good. Now what it's telling us here is that this one is saying we're a little bit above the ASHRAE benchmark. So in most of the United States, this would not pass code because it does not meet the building code standard for energy consumption. So we've got to make it better. And over here, it's saying the operating schedule, currently a range, it's testing it for 24/7 and 12/5. If I click on this circle thing, it shows me how that impacts. Now this is a house. It's probably 24/7. You know, that we need to keep the energy stable 24/7, especially in the days of the pandemic where we're staying home all day and all night. But anyway, so you know, so I could change that. I'm not going to change it, I don't think. I think, well, this is kind of important. So to be a little more realistic, you know, I can't go to a 12/5 schedule in a house because I live in the weekend. If this is a vacation house, I might want to change this, but I'm not going to change it. And since I know I'm not going to change it, I can move this over here. And let's leave it there. Now you see my energy costs went up. That's because this is an average. This is the mean of all the different possible energy costs based on operating schedules. Well, I know my operating schedule is in this area. So I'm going to keep it like that. And that made my performance worse in this case, but it's more realistic to what the actual building is going to be. So that's a good thing to do. Now it's saying the roof construction could really make a big difference. This is kind of surprising, but you know, but actually roof construction is a major factor in the energy consumption. So so I look at this, I can see that if I have a uninsulated roof, it's going to push my cost by 0.67. And if I have a R60 roof, so highly insulated, it's going to reduce it. It's actually going to reduce my cost by 0.09. So this is kind of the standard here, but it's between R10 and R15. You know, it's pretty easy to do high construction, and you see that the curve goes down dramatically here. So R38 is a pretty high construction, but it's easy to do in a roof. So knowing that, you know, I could push my construction over here, and you see I reduced my mean cost of energy. And I'm going to close this. And now you see I have three schemes. You know, I reduced the energy, the roof construction. I increased the roof construction R value, and that reduced the expected energy by that amount. Now, it's kind of useful to save each of these. So I'm going to add a scenario here, and I'll call it roof R30. Well, let's call it high insulation. So So it's kind of fun to save each scheme you do, each scenario you do. Now it's saying the next most important thing is my HVAC system. HVAC systems are kind of expensive, but let's look at this. We'll see that it's got a rather poor quality one here. And this one over here, the heat pump, is very high quality, high efficiency. And it makes a difference which one I choose. You see, they vary quite a bit. They keep moving down this line. So I could decide, let's go with a high efficiency heat pump or better. And you see it changed fairly dramatically. And I can look at that and watch it change from 160 down to 129. And I'll make a scheme for this, scenario for this. And I'm at 1.29, it's pretty good. So we're closing in on that 1.04 here. And now it says my wall construction might be something to look at. So let's look at that. We're here at R13 wood, various wall constructions. Well, we're not going to do uninsulated. So, or CMU. It's kind of tough. In South Africa, these brick walls are fairly common. So let's say there's going to be some insulation, but not much, maybe not much. We can move this around and see how it changes this cost up here. But let's assume our wall construction is going to be kind of bad. Not high insulation value. Our infiltration, you see it makes a pretty big difference. This is the number of air changes. Now, you heard Chris Mulder talk about how the lifestyle is very much outdoor. Big windows and sliding doors, they keep open. Okay, that pushes the air changes up a lot. So let's just leave this wide range of air changes here. We won't change that, even though it's really important. Okay, the wall to window ratio of northern walls. Remember, this is South Africa. The north walls face the sun. So I could look at this and say, if my northern walls, if I only have 9%, I'll be here. And if I have 80%, I'll be 0.16. Could look at those. It's kind of 80% is really a lot. So we may want to pull that down some. And we could sort of make a target. What if we had 65% walls, glass area, let's say 50% glass area. Let's do a little more than that, 65%. And we're not going to have 0. That would be dumb. So, what if we had 30%? So in that range, and that's giving us this mean cost of 1.27. So that pushed that number up a little bit, and we need to push it down. But, we're going to have those exterior, we're going to have windows on the north side. We know it. South walls. South walls, we don't really need much on the south, so let's push them down to here. And that pulled the energy cost down. Now I'm breaking my rule here. So let's make a scheme. Click on this and pull it out. Rename it. And you see how we push this down, and we're pushing it down a little bit more here in this view, but maybe not enough. Infiltration, we didn't change. The wall window ratio, window glass, we've got single clear, ranges from single clear to triple low E. So you'll notice that it doesn't change much. A penny difference. Low E glass is really expensive. So, let's leave that the way it is. We're probably not going to use the low E. It's too expensive. We could pull this up. It changed it by a penny. A penny worse. Okay. North glass, similarly, we could take that triple glazed, double low E out, and let's say it's not going to be single clear. So we'll pull that down and we get it back. So, so I'm changing my glazing. Oh, that's the ratio. Okay. Okay. So I'm going to go and change my other window glass. This one. It's not going to be single glazed. It's going to be at least double glazed. Probably not going to be low E because it's expensive. And this one too. And I'll make a scheme for this, or a scenario for this. Okay, we're having a hard time getting down to that 1.04, using kind of typical wall construction, infiltration, kind of skipped over that. Now, one way we could probably get better is let's look at the lighting efficiency here. So if we use LED lights, we're going to get much better efficiency. So and they're cheap now. So let's pull down to a fairly high efficiency lights, and we gained a penny there. And we'll make a scheme for that, or a scenario for that. Spell it right. I'm not going to worry with plug loads. Building orientation, could change it, but it's not going to make much difference, mostly because there's not much glass on this building. Shades, shading the windows isn't going to make a lot of difference either. So let's not bother with it. And so shading, what about on the west? Does that make a difference? Not really. There's not much glass on the west. If our design had more glass on the west, then this would start to make a difference. Now, finally, we get down to photovoltaic systems, PVs. If we wanted to add PVs, and Chris Mulder is very keen on putting PVs in all of the projects. He wants to generate energy. So we can go down here to surface coverage of PVs. Let's not worry about payback limit or efficiency at this point, and go with surface coverage. And this one is 0. This one's 60, that one's 75. So it's telling me it's not making much difference here. Bit odd. Because it's flat. Why is that? Let's go to payback limit. Now, I have to look at some things to see why that is. All right, so we're still above what we need to, how can we make this a better design, make it reach that ASHRAE standard? So, so we've got high efficiency heat pumps, good roof construction, wall construction's maybe not so good. Maybe we just need to do the wall construction better. That's really the thing that's going to make the biggest difference. So, so let's use a brick veneer with a pretty good wall construction. Pull it over to here. Now, our real cutoff is here. So let's do that. And that dropped us down to 1.13. So we'll give that a new scheme name. So IR value are wall insulation. This makes a big difference. So let's reduce the air changes. That got us down to 0.017. So we'll make a scheme for that. Almost there. Let's probably get it with these walls. So let's sort of pledge to reduce the amount of windows on the western walls. Did we do east already? Yeah, we did east already. So we're our strategy is to not have so much glass on the west. So and now we just make the ASHRAE 90.1. So, so the idea here is that we're playing with scenarios. We have not made a decision about design. We're identifying what the options are that are reasonable. You know, what the targets are. Then once we have those targets, we then make design decisions. So we're getting information, we're getting insight, we're getting analysis and advice from the computer to tell us how we should design here. You know, probably want to do these too. You know, having a lot of east glass is not a good idea either. So let's go with that. And now we're actually below the ASHRAE standard slightly. I have a extra one here, so I'll delete it. All right, and it shows our progress through this of making these decisions. So, you know, so we changed the operating schedule, we changed the roof construction, the HVAC, the wall construction, and it's giving us all of these seeing the impact of all of these decisions. Now, just to show you a couple of other interesting things, if I click on location here, I get my map. Here's our location. Crossways is right down here somewhere. Anyway, that's fairly close. And if I click on this, it gives me the climate data, which is kind of fun. It gives me wind roses and other kind of climate data. Mostly the temperatures. So the highs, the average, and the low. So these are the values being used in the calculations. Notice we're in the southern hemisphere, so the winter time is May through August. And you see that reflected in the temperature charts. You know, it's hot in January and February. It's cold in July. So by clicking on this, we can toggle back and forth between the building model and the climate. Now, if I go back to Insight here, yeah, I can toggle back and forth between those. Now, what I'm looking for is settings. And the thing I need here is the utility rates. And right now it's using an automated rate service, which probably is not giving us a number. That's why the photovoltaics are not working. So, I played around with this a little bit. Maybe I've shut down that window. So there are online tools that can tell us about energy rates. That's not all right. So let's call it about 100 cents per kilowatt average. Assume that's dollars. Dollars per kilowatt average. So, so South Africa, we're saying 93.8 cents. What is that? Is that, that's in Rand, right? Probably. So 0.09 in dollars. Term rate is, let's say, that reduced our cost here. I wonder if that makes, yeah, so that made a difference in our PV. So because it didn't have values for the electricity cost, then it really couldn't give us a value of photovoltaic energy. So with a value for photovoltaic energy, then I can play around with this. Let's say we put in 60% of our roof is a photovoltaic system. And then we can go up here and see our value here. If I change the scheme, add a scenario. We actually went up, which is weird. I don't quite know what's going on there. Yeah, well, I changed the utility rate, so that's why. But we still got, we're just above the ASHRAE amount. if we went to a little more, well, let's not do more surface coverage. Let's look at the payback limit. So if we're willing to, well, either 10 years or 20 years, doesn't matter. I don't want to go to 30 years. If I pull this up, my cost is going to go up quite a bit, but I don't want to spend 30 years paying back the it looks like I have to, maybe. Anyway, I can play with these and try to get a value that works for me. You go to efficiency and use a higher efficiency one. That's not going to make a big difference. Change my payback to at least 20 years. And now I'm back to the something that that works from ASHRAE point of view. And I'm going to call this adjust PVs. So I'm defining how much photovoltaic systems we need here. If I go to here, visualize, I can look at my PV analysis and I can see which parts of my roof are most effective. So if I click on one of these, it shows me that this this surface accounts for 22.75% of the roof. And I can click on multiple surfaces. And start to decide which roofs I want to use for photovoltaics. So the ones that have a, it's color coded by production. This is a flat roof, so there's not much difference here. But if we had pitched roofs, some of the sloped roofs would be more effective for photovoltaics than other ones. And we could start to design where our photovoltaic systems go, and how many we need, how much surface area needs to be photovoltaics. We might come back and decide that we don't have enough roof facing in the right direction. So that will affect our massing model. We change our massing, change our roof orientation, change the size of that roof, and now we get enough area facing in that direction to get the energy production that we want. So that's all pretty powerful. One last thing to show you. If I click on these dots here, then I can export the data. And so let's export, let's select all and get everything. Export. It's compressing the items and downloading them. Takes a few minutes. So here it is. It's a zipped file, so I want to unzip it. So I'm going to go to Open, Windows Explorer, Open. Let's pick everything. And extract to what? And if I go to my documents, share that. Take me a minute here. Y'all see that? And so it's loaded all of these charts. So, and it shows our comparisons here. We haven't yet met the Architecture 2030, but we passed ASHRAE. That's not even the right one. Don't know what it did. Oh, that's all. Just looked at all of them. PV surface coverage of 60%. So that's, you know, kind of telling us what we need to design for. You know, the plug load efficiency is a matter of which appliances you choose for your building. So, you know, if you use a high efficiency washer and dryer and range, Energy Star appliances, then you reduce your plug loads. You see it's pretty significant. Operating schedules, lighting efficiency, infiltration, HVAC systems, and then we're into the next thing. If we look at what it gives us, so it's giving us these tables of window glass, window shades, etc., all these different charts. It's also giving us the DO2 input file. So you could run DO2, which is Dr. Haverhill's favorite energy simulation tool, or you could run an Energy Plus file, which is Dr. Culp's favorite energy simulation tool, or Green Building Studio, which is another online energy simulation package provided by Autodesk. So it gives you a fair amount of information for doing your presentations. A lot of image files that you decide whether they're significant, whether you want to present them, but then you can place them on your Revit sheet by inserting an image. Likewise, you could take that solar analysis and show it. You can actually do it in Revit even. So Revit will tell you what you can expect to gain if you put PVs over the roof. And you'll notice that it actually, this parapet wall here would create shading on the roof, and it's taking that into account. You've got solar cells here that are not producing anything because they don't get any sunlight. So Revit can help you do your solar design. You'll notice that the shadow is coming from the north, and the sun is in the north and casting a shadow that's on the south side of the roof here. So it's accommodating the solar angles properly. You may know with Revit, so it's given us a whole kind of description of that that you can include in your presentation of your solar performance. If I turn the sun path on, I can even see a sun diagram of how the sun moves around that building. So you've got a lot of tools for doing energy analysis and refining these designs to be very low consumption of energy. And this, these next 2.5 weeks, I need you to get comfortable and familiar with that. That's what the main part of what this segment is. The water calculations are easy. The wastewater calculations are easy. Structural, I'm told, is easy, but I've never done it, so I don't know. I'll try it out. But these energy ones are kind of complicated, but you've got tools for doing it.